Let's see if we can rationalize why having high citrate would mean having high energy. So when you have a lot of citrate in your cell, you're going to be in a high energy state. And so we can think about this if we look starting at the electron transport chain in mitochondria. So we can think about it by looking at complex 5 or ATP synthase. So we have that down here. And if there is a lot of ATP in the cell, that means complex 5 won't be able to run and use ADP as a substrate. And that's because of the fact that the concentration of ATP plus the concentration of ADP plus the concentration of AMP is approximately equal to a constant in the cell. So if we have a lot of ATP already here, that means we won't have enough ADP to make that ATP. So in a high energy state, we have a lot of ATP, which means that we don't have as much ADP to act as a substrate for ATP synthase or complex 5. So that means that this complex can't run. And that means that all these protons that we have here that are being pumped into the intermembrane space won't be able to go back into the matrix. So these protons won't be able to come back in this way. This won't be happening. So what happens is you build up a really high proton gradient here, and in fact it becomes so high that complexes 1, 3, and 4, they don't have enough energy to pump those protons because this gradient is so high. The gradient isn't being depleted at all. It's just going to build up a lot since complex 5 or ATP synthase isn't running. So if complex 1, complex 3, and complex 4 can't pump protons into the intermembrane space, that means that this key reaction right here, this redox reaction of NADH getting oxidized to NAD+, that won't be happening. So we won't have NADH being oxidized into NAD+, and if NADH can't be made into NAD+, we're going to have high NADH concentration as well. So far we said if there's a lot of ATP, ATP synthase can't run, and then if ATP synthase can't run, that means that we're going to have this high proton gradient here, and it's going to be so high that complexes 1, 3, and 4 can't continue to pump protons because the energy that you get by oxidizing NADH to NAD plus won't be sufficient for the protons to get pumped. So that means we're going to be left with a ton of NADH in the matrix and virtually no NAD plus. And the reason why we have that is because the concentration of NADH plus the concentration of NAD plus is also equal to a constant, approximately. So now you may be thinking, great, okay, that's fine. So we have a whole bunch of NADH now. We have a whole bunch of NADH in here and not that much NAD+. How is that relevant to citrate? So for that, we're going to have to look at the citric acid cycle or the Krebs cycle or the TCA cycle, whatever you want to call it. So we have to look at that to see how a high concentration of NADH is going to affect the cycle. So you can see three places where we have NADH. We have it at isocitrate dehydrogenase, so right here. Then we have it at alpha ketoglutarate dehydrogenase complex, and then we have it at the malate dehydrogenase enzyme. That's where we are making NADH. And remember, this is happening in the matrix, and we just said here we're going to have a high concentration of NADH in the matrix. So this was a high concentration of NADH, and we were in the matrix here. So since the citric acid cycle and the high concentration of NADH are both going to be in the matrix, we can rationalize how this will lead to a buildup of citrate. So isocitrate dehydrogenase needs NAD plus to make NADH, but we said there's virtually no NAD plus. So virtually no NAD plus, but lots of NADH. So if there's no NAD plus, isocitrate can't be converted into alpha ketoglutarate. So this step won't be happening. And if that step isn't going to happen, that means we're going to have a buildup of isocitrate. So isocitrate builds up. Citrate is converted into isocitrate via the enzyme aconitase. What's interesting about this delta G is that it lies far to the left. So citrate to isocitrate favors citrate. So when we have a buildup of isocitrate, this is going to go actually towards citrate. And that's going to lead to a buildup of citrate. So basically what we had here is isocitrate can't convert into alpha ketoglutarate via the isocitrate dehydrogenase enzyme. And so you have isocitrate buildup. And isocitrate likes to be in the form of citrate rather than isocitrate. So this equilibrium lies far to the left, so we have citrate buildup. So in this way, we can rationalize why high energy is going to mean high citrate and vice versa, why high citrate will signal high energy in the cell. So that's kind of cool how we can go all the way from the electron transport chain and rationalize it all the way back to the TCA cycle.